chapter 4 here. So we talked about in chapter 4 the experiments that led to the understanding of the atom and sort of the structure of the atom. Um, we talked about Thomson and his experiments with the CRT tube, also Milligan and his oil drop experiment, which were two sort of important experiments for our understanding of electrons. It's really the mass of the electron sort of came out of those experiments. An early model of the atom, which again was proposed by Thomson, which is the plum pudding model, where they thought that the whole atom there was pretty much all positive charge, which electrons sort of embedded inside, and most of the mass of the atom being the electrons. And this was sort of disproven by another really important experiment, which was Rutherford's experiment, the gold foil experiment. He shot alpha particles, which are positively charged radioactive particles, at pieces of gold foil and other metals. And he thought, based on Thomson's model, that most of them would go through, but there would be a little bit of deflection as they kind of went through, again, shooting something positive at an atom that's positive. Um, and they were kind of surprised based on the results. They saw that most of the alpha particles basically just sailed through with no problem. That basically meant that they pretty much hit nothing. Every so often, they did see these positively charged alpha particles be bounced off at these large angles and even back at the source. And that made him think that it had to hit something that was very, very densely positive. So, sort of the results there of Rutherford's experiment was we throw out basically the plum pudding model and come up with a new model of the atom, which is sort of the current model of the atom, which is that the atom is mostly empty space, which is why most of those alpha particles basically sail through with no problem. It does contain a dense positive core, which is the nucleus, and that accounts for why those guys basically bounced off at really large angles. And inside the nucleus, it was later found to have contained the protons, which are positively charged. And in 1930, it was also found to contain neutrons by Chadwick, which are no charge. And so we have sort of our version of the model here, which is atom is mostly empty space. Within that empty space is essentially where we have electrons sort of traveling around in a random sort of pattern. We have a central nucleus, which is basically positively charged because it contains protons. And the other main difference, obviously, between the sort of current model and the old model of the atom is that most of the mass of the atom is made up of the nucleus. And that, again, is because the nucleus contains both protons and neutrons. And both of those things, a proton or a neutron, is about 1,876 times heavier than any electron that's basically flying around. So that does make sense since both protons and neutrons are quite heavier than an electron, that most of the mass of the atom is made up of the nucleus. In terms of those three particles, protons, electrons, and neutrons, the neutron is the heaviest out of all three. It just barely inches out the proton. So the neutron is very heavy, proton almost just as heavy. We're talking, you got to go to like the third decimal place to see the difference. They're about the same amount in terms of mass, but actually a neutron is slightly heavier, followed by a proton, and then a electron, as I mentioned, much, much lighter, about 1,800, almost 1,900 times lighter than both of those particles individually. So with that in mind, we talked about some important aspects of an atom, and that being some things that we sort of finished up on, which was isotopes here. And isotopes are really the same element, but they have different mass. And the important thing in terms of identifying the element you're talking about is actually the number of protons. So the number of protons is what really determines what element you're talking about. And we can find a number of protons on the periodic table, and that is what is referred to as the atomic number. So the atomic number, as we talked about last time, which is abbreviated with a Z sometimes, is the number of protons that you find in an atom. And again, if you look on a periodic table, it is the number that is above the symbol on all those. And as we talked about last time, if you are looking at a periodic table, you will not see any of those numbers repeat, which means every individual element has its own number of protons. And that means that if you know the atomic number or the number of protons, which is essentially the same thing, you essentially will know what element you're talking about. Or if you want to figure out the element, or you can look at the periodic table and really find the atomic number. Now, if it is neutral, again, because really there's protons that are positive in an atom and electrons which are negative in an atom. If the atom is neutral, the atomic number will also tell you the number of electrons that has to be there to balance it out. But as we talked about last time, an important distinction is the actual definition, though, of atomic number is just the proton. So it will tell you secondarily that if it's neutral is how many electrons you have. But if you're asked, again, a question of what is the atomic number mean, it is actually just the protons. So the other important sort of number that we talked about at the end there was the mass number. And the mass number is the number of protons and neutrons that you find in an atom. And that is abbreviated with an A, like we see on the screen there. And the mass number is not found on the periodic table. So that number that's underneath the symbol is not the mass number. It is what is known as the atomic mass. And what confuses people is sometimes that number is very close to the mass number they're trying to find. One thing to remember and to help you remember that is when you're asked to calculate either the atomic number, the mass number, number of protons, electrons, or neutrons, they all should be whole numbers. So one way to remember that is obviously if you look on the periodic table, all the numbers underneath the symbols, they're pretty much not whole numbers. They're all decimal sort of numbers. So those are, again, not the mass numbers or anything like that. One way that we do represent isotopes, which are essentially the same element but with different mass, again, because they are the same element, they would have the same number of protons. But what gives them the different mass is the number of neutrons that they have. Is we can represent the symbol like we see on the screen. Top left of the symbol is typically where we put the mass number. Bottom left is where we put the atomic number that we could get from the periodic table. So that, again, is one way that we could represent that. Again, just in terms of isotopes, so for example, if we looked at, say, something like hydrogen, there's hydrogen, which, again, is sort of an exception to all the other elements. Hydrogen has one proton and no neutrons. And so all other elements will have neutrons, protons, and electrons, but hydrogen has one proton and one electron and no neutrons. There's what's referred to as deuterium, which is basically heavy hydrogen. It has one proton and one neutron. And there's tritium, which is basically the radioactive version of hydrogen, has one proton and one neutron. And if we were to write sort of our symbols for all three of these guys, if we wrote it for hydrogen, it would be H because it has one proton. It also has no neutrons, so 1 plus 0 is 1. So that would be hydrogen symbol. Deuterium, which is, again, sometimes referred to as heavy hydrogen. We know the symbol is still hydrogen because it still has one proton. And in this case, 1 plus 1 is 2 for the mass number. And that would be the symbol for deuterium. And tritium, again, we also know, even though it's got a different name, in this particular case, we do know it's still basically hydrogen because it has one proton. And again, the symbol here would be 1. And 1 plus, that's bad math there, 2 neutrons is what he has, would give you 3 for the mass number. And that would be the symbol for tritium here. Again, they're all basically hydrogen, even though they got some different names. And we know that they're hydrogen because they all have one proton, which means that they are all the same element, but they all have different neutrons, which is why the mass number, the top number, is different. So again, if we take the top number minus the bottom number, 1 minus 1 gives you 0. 2 minus 1 gives you 1 neutron, and 3 minus 1 gives you 2 neutrons. So that is the way that we can definitely figure out, the number of neutrons, really top number minus bottom number. Any questions on that there? So I think we talked about some of this, but just again, a little reminder here. Oops, come back. Our bottom number there, which is bottom left of the symbol, is the atomic number. And again, that is the number that you can find on the periodic table. The actual definition, as we've been talking about, is just the number of protons. But again, if it does not have a charge, and we would look for a charge somewhere here, and we don't see anything written there, so we know that it's neutral. Again, it will tell you the number of electrons, but again, that's not part of the definition of what atomic number means. And the protons are the atomic number is the most important in determining the element. So if you look on the periodic table, you'll never have a sodium atom with an atomic number of 9 or 9 protons. And that's because if you look on the periodic table, number 9 is fluorine. So it'll be fluorine because it has 9 protons or an atomic number of 9. The mass number, as we talked about, is the number of protons plus the number of neutrons. And again, in terms of the symbol, it is put there top left of the symbol. And that is really what makes our isotopes. That is what gives them the different mass that they have, is the different numbers of neutrons that are present. Usually always a bigger number than the atomic number. The only exception is hydrogen, which they have the same. It's one on top, one on the bottom, because it has no neutrons. But everybody else will have typically the bigger number up on top and smaller number on the bottom left there for our atomic number. So here, if we look at oxygen, we got 16 on top, 8 on the bottom. So right away, looking at that, we know that it has 8 protons, as that's the atomic number on the bottom. Again, we do not see a charge here. So we know in order to balance that out, it also would need 8 electrons. So 8 positives, 8 negatives give you 0 for the charge. And in terms of the number of neutrons, again, we would take the top number minus the bottom number. So that is 16 minus 8. And that also is 8, I believe, as well. So what would happen if something, for example, did have a charge? So let's just say we took this same guy here, identical to this guy, except that we give it a -2 charge. So one thing that stays the same, obviously, in this case, is we look at the atomic number here, and it is 8, which means this guy here still has 8 protons, which are positively charged. It has to be 8, right? Because it is still oxygen. We can't change the protons. We actually do our neutrons just like below. Our neutrons in this case would still be 16 minus 8, which would be 8 neutrons. So you can see here that when this thing does gain a charge of -2, the only thing that will change is actually the number of electrons. So it is the number of electrons that change. And in this particular case, it would actually have 10 electrons. So 10 negatives and 8 positives leaves you a -2 left over. And that is where that charge comes from. This is what is known as an anion. It has gained electrons. The original guy with no charge had 8 electrons. Guy with the charge has 10 electrons, and the negative means that it gained electrons. So an anion is a negatively charged ion. An ion is a substance that has obviously a charge associated with it. And an anion is made by gaining electrons, as you can see here. So something sort of gains a charge, either positive or negative. The only thing that's affected is the number of electrons. Again, the protons cannot be affected because that determines the element. So if you change the protons, you change the element. So it is just the electrons that change if something gets a charge. Question on that? Okay, so let's take a look at another example here. Here's our calcium. Again, looking at the bottom number, which is our atomic number. Again, looking here, we see no charge. So that tells us the atomic number is 20, which means it does have 20 protons. Also, because it's neutral here, it would have 20 electrons. And in this case, our neutrons would actually be 40 minus 20, which would be 20 as well. They don't always end up being all three the same number, just kind of coincidental here. So we got 20, 20, and 20 on that. And again here, if we had calcium that actually did gain a charge, say a +2 charge here, which is what calcium gains. And in this case, something with a positive charge is what is known as a cation, a positively charged ion. And the same sort of process here, we would know just like below that it does have 20 protons because that's the atomic number. We also would have, in terms of neutrons, the same. It would still be 40 minus 20, which would be 20 neutrons. So just like the last one here, it is the electrons that change when it gains a positive charge. And in that particular case, we're going to have actually 18 electrons. 20 positives plus 18 negatives leaves you a 2 positive left over. And that is where the charge basically comes from. And a cation, as you can see, if you compare the neutral guy started with 20 electrons. The one with a +2 charge has 18 electrons. It actually lost some electrons here. Is how we make a cation, which is a positively charged ion. The charge actually tells you something when you see a charge like this. The positive tells you you lost electrons. The 2 tells you how many you lost from the neutral. So plus tells me I lost electrons. 2 tells me from the neutral guy, I lost 2 electrons. Same idea with the negative, works the same way on the previous one there. If we take a look at that one more time. The negative here tells you you gained electrons. And the 2 tells you how many you gained. And again, looking at our original, started with 8. Our guy with the negative charge gained 2 electrons from it. So the actual charge, the number, and whether it's positive or negative will definitely tell you what's going on in terms of electrons, in terms of either gaining or losing. Now, if they don't state that something has a charge, the protons and the electrons will equal each other. So here as well, if this guy is neutral, which we assume it is unless otherwise sort of stated, or you see an actual symbol or something like that, we got 35, which is the atomic number. This is off, I think, the way it's written here. It should be a little bit to the left there, and these guys should be left. But 35 is our atomic number, which again is our protons. And in this case, because it's neutral, we don't see any charge written here. It would also be 35 electrons. So essentially all of our positive guys, which are protons, all of our negative guys, which are electrons, balance each other out to no charge. And then in terms of our mass number, which is 80, minus 35 would give you 45 neutrons. I'm not sure on this one. I think they're trying to show you something weird, but you probably won't see it written like that. You will most likely see it written like this. Or as we talked about last time, you will most likely see it written like this. And the BR-80, again, when it's written like this is the mass number. And again, I'm not quite sure what the book was trying to show here, but usually these are the two ways that you write it and how you see it in this sort of form. And again, if it was written like this, you would go to the periodic table to find the atomic number. And again, if you go to the periodic table, that's where the 35 comes from. Again, the symbol up on top of the guy there would be it. So for example, bromine normally makes a -1 charge. And when it does make a charge, and if we had sort of the same setup here, what this would mean is in terms of protons, we would have 35. In terms of neutrons, we would still have our 80 minus 35, which is 45. And in terms of our electrons, the way you could look at this is negative tells you that it gained electrons. It's a -1 charge, which means it gained 1 electron. So the simple way to do is take 35 and add 1 to it. It would need 36 electrons, giving you that -1 left over in terms of the charge. So again, if it does have a charge, it would be indicated either in the symbol or it would tell you, hey, this thing has a +2 charge, -3 charge, or something like that. All right, so why don't you give this one a go here. We want to figure out the protons, electrons, and neutrons in this guy here for silver. See what you come up with. Okay, so if we look here, we got our atomic number, which is on the bottom, which is 47. So that is going to be our number of protons, which would be 47. We have our mass number, which is up on top. So that's going to help us with our neutrons. So we're going to take 108 minus 47 here. And that's going to give us, it looks like 61. And in terms of this, again, we do not see a charge here. So we know that our number of protons should equal our number of electrons, which would also be 47 as well. Any questions on that particular one? So it looks like perhaps it is B. It looks like perhaps, I think, 47, 47, and 61. Again, nothing written there, so we assume that it is neutral. All right, so do this one here. Okay, so on this one here, again, we see no charge happening here. So number of protons will equal the atomic number, which is our bottom, which is 25. Also, because there's no charge, that will also equal our electrons in this particular case. And now if we take 60 minus 25, we get 35, it looks like. So number of neutrons, again, will be mass number minus atomic number, which is 35 in this particular case. And that is number, looks like, where are we at there? They did backwards right there, I think. Number C, or letter C, is the winner, I think, in terms of that. Or no, it is actually D is the winner. 25, 25, and 35. So B it is. Again, if this guy did have a charge, so if we had our same guy here, but he had a +4 charge, in this particular case, what that would mean is we would still have our 25 protons. We would still have, in terms of our neutrons, 60 minus 25, which would give us 35. And in terms of our electrons in this case, the positive means that it lost electrons. The 4 means that it lost 4 electrons. It would have 21 electrons in this case. 25 positives, 21 negatives, leave you a +4 left over when it's all said and done. So again, just the electrons are going to be changed here. Any questions on those there? Okay. So the nice thing about isotopes, as we sort of been talking about, and obviously you need to be able to do mass number, atomic number, number of protons, electrons, and neutrons. The nice thing about isotopes is that they do have the same number of protons, which essentially means they are the same element, and they will perform the same type of sort of chemistry, if you will. So sometimes the benefit of using isotopes, especially in, say, experiments, is we can sometimes use a radioactive version of an element, and we could use that radioactivity and sort of follow what's happening with the radioactivity to sort of follow something, for example, like copper. I used to do experiments with radioactive copper. Nice thing about the radioactive version of copper and the regular version of copper is it sort of does the same thing in the body. So you could actually just follow where it went in a sort of mechanism or something like that in a process by really just following the radioactivity. So sometimes that's very helpful. Obviously, sometimes radioactive isotopes are used for treatment of diseases, and also obviously for imaging and stuff like that. So a lot of times it's very useful, some of the isotopes that we use. Now, here again, it's just sort of a picture of what we were talking about here. These are, again, two isotopes of sodium, and they both need to have 11 protons. Otherwise, they would not be sodium. So here it is just the neutrons that are different. And you can see in one we have 12 neutrons, and one we have 13 neutrons. And if we add our protons and neutrons together on the left there, that's 12 and 11, gives us 23. And if we add our protons and neutrons on the right, that's 13 and 11, which gives us 24 for our mass number. And as we can see, those are the numbers on the top here. And obviously the bottom number, which is 11, can come from the periodic table. And here's the three sort of isotopes of hydrogen, as I wrote earlier. Again, the first one is hydrogen. Second one is what is referred to as deuterium, which is heavy hydrogen. And the last one is really the radioactive version of hydrogen, which is tritium. And again, they are all hydrogen because they all have that one circle of protons in it. And you can see that they have different numbers of neutrons, which does give them some different properties, obviously, as well. And you can see, again, that hydrogen is the only element that does not contain a neutron. That's why hydrogen has some special sort of properties. Again, hydrogen has just one proton and one electron, no neutrons, but everybody else will have all three of those things.
Hey, I have a question.
Yeah.
So what makes the mass number increase?
The mass number increases because the mass number is the number of protons and neutrons.
Mm.
And the protons will remain the same for an isotope, no matter what. So it is the number of neutrons actually change. And there's different ways that these sort of can be achieved, if that's more what you're asking, how you could kind of get different neutrons. It's just sometimes that it appears naturally. So there are natural isotopes of different elements that just have extra neutrons in them. And you can also sort of man-make it, if you will, through sort of a nuclear process where you could kind of hit it with some different particles, and sometimes that will change the number of neutrons that occur there.
Mm-hmm.
But just naturally, there are isotopes of many elements that just naturally occur that way, that they have sort of different numbers of neutrons.
Okay, got it.
Yep. Other questions? Okay. So here again is another example. These are another example of isotopes of carbon. One is the carbon-14 isotope, and that's how it's sometimes worded, 14 being obviously, again, the mass number. And this is the carbon-12 isotope, the 12 being the mass number. And again, the guy on the left there, they're both left and right going to be carbon. So they both have the same atomic number, which is 6, the number of protons. And again, to find our neutrons, which is really the only difference between these two guys, 14 minus 6 for the first one, they're going to give us our 8 neutrons, and 12 minus 6 can give us our 6 neutrons there for carbon. And again, isotopes of each other. Same element, different numbers of neutrons, which gives it a different mass. Yeah, so the The isotope or an isotope is really uh, the same element, if you will. So they're not really necessarily different elements. They're the same elements. But if your question is more like, will you be able to tell the difference in terms of mass number or neutrons and those type of things, you will for questions like this. So you will have information or enough information given to you to figure out the mass number or the number of neutrons will be given to you. So you'll have some type of information given to you to help you sort of identify the isotope you're speaking of. So for example, these two here, which are considered isotopes, they're both the same element. So both really carbon by itself. So when we think about elements, and we'll talk a little bit more about this in another chapter, but when you look at elements, for example, on the periodic table, and you look at it and go, oh, that's the element carbon. There's really no element that is carbon like you see on the periodic table, it's just a C. There's either, for example, carbon has two isotopes that naturally occur. There's actually the carbon-12 isotope, which we see on the right. The carbon-12 isotope occurs like 98% of the time naturally. And there's actually the carbon-13 isotope, which occurs about 1.1% of the time. So when we actually look at the periodic table where it says C and we go, oh, that's the element carbon, that C really represents the naturally occurring isotopes of that particular element. So that C could represent the carbon-12 isotope, or that C really represents carbon-13 isotope. But we sort of think of it as there's just a C out there by itself kind of moving around. But the element itself is a version of an isotope, basically. So all elements are made up of naturally occurring isotopes that have the same number of protons, but different numbers of neutrons. Other questions on that? So why don't you give this guy a go here and see what you come up with. We have a certain isotope that contains 23 protons and 28 neutrons. What is the mass number? What is the element? So again, a periodic table would be helpful here if you have one. Okay, so here where we want to start is we're not sure what it is. We can kind of do the symbol here. So 23 protons is the atomic number. So that'll be 23. And that number is important because if we go to the periodic table and we find number 23, it will tell us that that is the symbol V there. And again, that would be 23. Our mass number would be our protons and our neutrons. So 23 plus 28 gives us 51. So this right here would be the correct symbol and our mass number and atomic number. Questions on that one there? Okay. So I want you to do this one. A certain isotope X plus contains 54 electrons and 78 neutrons. What is the mass number of the isotope? See what you come up with here. Okay, so let's take a look here. So on this one, we actually do have a symbol here, and it does have a positive charge. So a positive charge, as we've been talking about, means that it did lose an electron. And that is important here because they do give us the number of electrons, which is 54 electrons. And that means in order for it to have lost an electron, it actually had to have one more proton, which is positive. 55 positives, 54 negatives gives us a +1 that is left over. And that's important because if it had 55 protons, that would tell us that the atomic number is 55. And although it didn't ask for it, this is cesium here on the periodic table. And that also is important because if it has 55 protons, the correct number for the mass number would be 55 plus 78, which gets you, what does that get you? 133, I think. Yes, maybe. 55 plus 78, 133 for our mass number. So here again, the charge is important because it tells us that it lost an electron, which means it has 54 electrons, but must have 55 protons. So the correct guy would be 133 in this particular case. Question on that there. All right, any questions on how to identify protons, electrons, neutrons, mass number, atomic number, all those things? Okay, so let's talk about then the periodic table. So again, if you have one next to you, probably would be kind of helpful, I think. So the periodic table is obviously the arrangement of all the elements that are present. And we talked about some important parts of the periodic table, but a couple important things. A period on the periodic table goes from left to right. So on a lot of periodic tables, if you look right around here, there's some numbers like 1, 2, 3, 4, 5, 6, 7. It's up. Sorry, I started a little low there. 1, 2, 3, 4, 5, 6, and 7 going that way. And again, periods heading in this direction. Groups go up and down on the periodic table. So up and down on the periodic table. And when we talk about groups, there's a lot of different numberings that you oftentimes will see on the periodic table. There's sometimes the A numbering, sometimes the B numbering, sometimes it just goes 1 through 18. We typically use the A numbering for our groups, and that's sometimes referred to as the representative numbering, this being group 1, this being group 2. We skip the middle part here. This is group 3, 4, 5, 6, 7, and 8 over here. So 1, 2, skip the middle. 3, 4, 5, 6, 7, 8 in terms of the group numbers. Now, important thing about group 1 here is, although hydrogen is hanging out here, it is not part of group 1. So hydrogen is not part of group 1, even though it's on most periodic tables. Group 1 actually starts with lithium. Is actually the first member of group 1 is lithium. Now, the periodic table, on top of the symbol, as we talked about, is the atomic number, which is our number of protons. On the bottom of the symbol, as we also talked about, is our atomic mass. And really, the periodic table is broken up into 3 categories. There are metals, nonmetals, and metalloids. On most periodic table, there's kind of this staircase still that comes down. And really to the left of the staircase are metals. These guys down here are also metals. To the upper right of the staircase is our nonmetals. And on that staircase, which is here in kind of blue and sort of translates up here, right about here, and coming down and across, going to move in that way. Those are what are known as metalloids, and they're also sometimes called semi-metals as well. They do have some different characteristics. Metals are good conductors of heat and electricity. They are usually very shiny, and you can pull them into wires and stuff like that. Nonmetals, on the other hand, are bad conductors of heat and electricity. They're usually very dull and brittle. In addition, in terms of metals, they usually are pretty much all solid except mercury, which is a liquid. And that's why on a lot of periodic tables, mercury will sometimes be a different colored letter. Nonmetals, though, they have a wide variety of sort of states. Some are solid, some are liquid, some are gas. And a lot of the nonmetals are those diatomic molecules that we talked about, like H2, N2, O2, all those guys are some of our diatomic guys. This is also the reason why hydrogen, which is right here, and we'll go back this way just to illustrate that, I suppose. Hydrogen is right here. And if you look at hydrogen, it is actually a nonmetal. So hydrogen is a nonmetal, and that is why it's not part of group 1, which is technically all metals. So hydrogen, because it has some unusual properties, sometimes found over here on 1, years ago on older periodic tables, they would actually put hydrogen on both sides sometimes. You'll sometimes see it if you look at an older periodic table. But hydrogen is a nonmetal, even though it's really hanging out. If you also look at the atomic numbers and follow the atomic numbers right about here, the numbers really jump. And that's because this row right here, period, should actually go right there on the periodic table. And same thing if you go right below it, the number jumps from there to there. And this guy should actually go right there as well. So these two guys on the bottom here, which are the lanthanides and actinides, they actually go right about there on the periodic table. And that's why they're called lanthanides and actinides, because those are the elements that they follow on the periodic table. So they're usually set on the bottom, otherwise periodic table is super wide if you put them in the sort of the right location. So really these two periods technically go right into here. Now, there are some groups on the periodic table that have a certain name, and if you're old like me, nobody really calls them families too much anymore, but they are sometimes called families. Group 1, which again is right here, starts with lithium, is the alkali metals. Right next to where beryllium is our alkaline earth metals. Heading over here to group 7, those are our halogens, and those are our guys that are those diatomics like F2, Br2, Cl2. That's how they naturally come. And group 8 is our noble gases. Noble gases means that they are chemically inert. They're not very reactive with others. They really don't react with other things. They react with themselves, but not other things. Couple other important things here on the periodic table between group number 2, which is where beryllium is, and group number 3, where boron is. These are the transition metals. So all these guys kind of in this area here are our transition metals. And transition metals, as we'll talk about when we talk about naming, they could have a variable type of charge associated with them. And they are metals. And that's why, as I mentioned just a second ago, that these two on the bottom technically go into here. These are sometimes what are referred to as the inner transition metals because they technically should go in there. We don't really do too much with these guys on the bottom. A lot of them are radioactive sort of isotopes, and nuclear chemistry do a lot with it. Probably the only element you might come across a lot on the bottom there is uranium, which is U, so that pops up a lot, but not too much going on in terms of those. So we have metals to the left of that staircase, which again are shiny, good conductors of heat and electricity. We have nonmetals, which is upper right of the periodic table of that staircase, which are dull, brittle, bad conductors of heat and electricity. And on that staircase, which is where our metalloids are, these are, again, sometimes called semi-metals as well. So semi-metals, metalloids, sort of the same deal. And what semi-metals or metalloids have sort of in common is that they have basically the same characteristics that would be classified as a metal and a non-metal at the same time. So if you're talking about a specific element that's in that metalloid region, it has some characteristics that are very much like metals, like shiny, good conductors of heat and electricity. And that same element has some characteristics of non-metals, like they're dull, they're brittle, they're bad conductors of heat and electricity. So the same element sort of has properties that fall on either side of them, and that's why they're sort of in the middle. As you transition from metals to non-metals, you have this staircase where members of that staircase have characteristics that can fall on either side. They have characteristics that can fall as metals, have characteristics that can fall as non-metals as well. Question on the periodic table there. Again, you do need to know which way groups go. You do need to know the groups 1, 2, 3, 4, 5, 6, 7, 8, where they are. You need to know where transition metals are. You need to know where metals are on the periodic table, where non-metals are on the periodic table, where metalloids are. And obviously, you need to know the special names. So group 1 is the alkali metals. Group 2, the alkaline earth metals. And by the way, alkaline means basic. And that's where a lot of strong bases come from, things like sodium hydroxide, potassium hydroxide, group 1 and 2. So that's really what alkaline means. It means something that's basic. And a lot of our really strong bases in chemistry do come from those two groups. The halogens on the far right there, number 7 group. And again, noble gases being number 8. Any questions on that there? And again, let's officially talk about some of those characteristics. Here again are some physical properties of metals. As I mentioned before, they're very good conductors of heat and electricity. You usually can hammer them into sheets. You can pull them into wires, and they usually have a very shiny appearance. And as I mentioned before, pretty much all metals are going to be solid, except for our good friend mercury, which is a liquid. So everybody else pretty much solid. And by the way, if you do have something like iron metal by itself, as we talked about, it is monoatomic, which just means it comes as iron. By the way, does not have a charge. So if you pull anything off the periodic table by itself, uncombined, it does not have a charge. So copper doesn't have a charge. Calcium metal wouldn't have a charge. There's no charge with anything. Things only really do gain charges once they start gaining and losing electrons by coming together. So metals really only gain a positive charge once they start binding with our nonmetals. All right, so which of the following statements is false? So fluorine is a halogen, and if you look on the periodic table, you will see F under group 7, and group 7 is the halogens, so that is true. Fluorine is in period 2 of the periodic table. Again, if you look at the periodic table and you look at the far left, there should be maybe a little 2 there. If not, if you count where hydrogen is, so that's period 1, going right below it where lithium is and across, that is period 2. And if you go across, you will see fluorine sitting there. Fluorine is a metal. That is not true. Fluorine being upper right of the periodic table, upper right of that staircase means that it is actually a non-metal. So fluorine is a non-metal, and fluorine is in group 7, and it is in group 7. So again, if you look above fluorine on the periodic table, it should have a number, either say 7A, it may say 17, but technically that is what we call group 7. Even though it is A numbering that we use, most people do not use the A, so most people don't say 7A or 6A. Most people just say group 5, group 6, group 7. It's implied that it is the A numbering, as again, in most chemistry classes you'll ever take, that is the numbering that you use. So the wrong one here is fluorine is a metal. Fluorine, again, is a non-metal, and those non-metals, like fluorine, the way they naturally come is as F2 in their natural state, just like everybody there in those halogens, Cl2, Br2, I2. This again is how they naturally come by themselves. A couple of other nonmetals that come like that, as we talked about, are these guys, H2, N2, O2. That is naturally how you find these guys. Again, none of these guys have charges. These are all what we were talked about, I think, earlier on, which are known as diatomic molecules, basically made up of 2 atoms together. So fluorine looks something like this. Question on that there. So when we talk about some reactivity of some of these elements, most elements are very reactive. Elements are generally found in their uncombined form. Exceptions are noble gases and noble metals. So noble gases, which is our group A, so that's your helium, your neon, your argon, your krypton, your xenon, all your ons there. They are chemically inert, which means they're not very reactive. They will combine with themselves, but not others. And there's some metals that are also what are sometimes referred to as noble metals. So gold is an example of that, Au, platinum, and silver. These are pretty much unreactive metals. They really don't react with very many things in normal situations. So that's the idea of what the word noble means. Is oftentimes referred to as a class set apart. So they sort of set apart themselves from everybody else. They really don't participate in a lot of reactions because they're not very reactive. And kind of jumped the gun here, but again, here's some of those diatomic molecules, which again, as I mentioned, are how these guys naturally come. So somebody says, hey, you have hydrogen or molecular hydrogen by itself, it is going to be H2, which is hydrogen gas. Somebody says, hey, you have molecular oxygen, it will be O2. So really, these are our halogens, as I mentioned before, how they naturally come. And again, these are 3 common gases, obviously, that's how they naturally come. And again, these are all non-metals here. And some of them are gases, some of them are liquids, as you can see here. So our non-metals have some different sort of properties associated with it. And again, here's our diatomic molecules, 2 nitrogens together, 2 oxygens together. And again, no charge or anything like that. So somebody says you have oxygen gas or molecular oxygen, the correct way to write that is O2, not just O. So there is no O by itself like that, one of them. So it doesn't happen. The only O that is by itself has a charge associated with it, which is an ion. But if it doesn't have a charge and it's just the element by itself, for something like oxygen, it should come as O2. Just like H, same deal, should come as H2 as well. Now, when we do have different forms of an element, those are what are referred to as being allotropes. And allotropes are really the different forms of a particular element. So carbon is an example of that. Carbon can be a diamond, it could be graphite, it could be something known as a fullerene. And they're all basically carbon. They're the same element, I think you get different responses depending on which one you give. It's like, hey, here's a pencil, it's carbon, as opposed to, say, a diamond, right, which is also carbon. So a diamond has sort of a different orientation of the carbon atoms. Graphite has the carbon atom sort of in sheets, and fullerene is sort of this 60 or more carbons that come together. It's sort of thought of as like looking like a soccer ball, sort of how it comes together, all those carbons and stuff like that. As you can see here, this is the way diamond is sort of arranged. Again, all the carbons are sort of arranged in this orientation, as opposed to graphite, where we get these carbons kind of in sheets and layers. And here, again, it's kind of like a soccer ball sort of arrangement of 60 or more carbons, which is what is known as a fullerene there. And again, obviously different arrangements of these guys, even though they're all the same elements, does have different properties. So obviously a diamond has different properties than graphite in that sense, than say a fullerene. So an allotrope, same guy, just different arrangement of those atoms. So the element that exists as a solid composed of a diatomic molecule at room temperature. So again here, it would definitely have to be one of our guys here, as we just saw, because silicone, again, is not a diatomic molecule. So the answer would be iodine is actually there. We actually saw it the other day when we saw that video where she took the iodine crystals and she heated it up in that beaker and made that purple, right? That nice purple fumes that came off and all those crystals that formed on the bottom of the evaporating dish. Chlorine is a green gas, and this guy is kind of a brownish sort of liquid and stuff like that. So the correct answer here would be iodine. And again, we saw that in that video where it grew all those crystals on the bottom of the evaporating dish that had the ice in it. And that was the iodine in that case. So we talked a little bit about this, but just to officially talk about ions. Ions are, again, things that have charges. And as we've been talking about, there's really two types of ions. There is a cation, which is something with a positive charge, and there's an anion with something with a negative charge. And as we've been talking about, cations, as we saw, is from a loss of electrons. And really what that means is when it loses electrons, it then has more protons than electrons, and it has a more positive charge, while anions is a result of gaining electrons. And the result of that is it now has more electrons, which are negatively charged, than protons that are positively charged. So we end up with that net negative charge. And these are atoms that have the same number of protons. Again, that makes it the same element, but different numbers of electrons. And we never change the protons, as we've been talking about, again, because if we change the protons, that means that we are changing the element, because the atomic number would change. So we do keep the protons the same, and the atomic number stays the same as well. In normal chemical reaction, really the only things that get affected are the electrons. As we talked about, electrons are on the outside of the atom. So when two atoms come together, the first things that come in contact with each other are electrons. And again, a lot of bonding is obviously based on electrons either being transferred or electrons being shared. So in a normal chemical process, we really don't touch anything in the nucleus. We don't touch the protons or the neutrons. That does definitely happen in nuclear chemistry. Those things change, but in normal chemical reactions, they do not. So as I mentioned before, cations are formed when we do lose electrons. And the guys that typically will lose electrons are our metals. Our metals typically will give away their electrons and become positively charged, our cations. So again, here's an example of magnesium. It's got 2 electrons. Those 2 electrons get lost or given off, and it becomes a positive 2 charge. So one way that we could represent that in an equation form is magnesium. When it loses its 2 electrons, it becomes a positive 2 charge, and we get 2 electrons on the product side, or the right-hand side of the arrow. And this indicates that electrons are lost. And this is the way that we sort of represent it in a chemical reaction. such as this, where on this side is our reactants, is the guy with no charge, and on our products, which is on this side of the arrow, we have our guy with the charge, and our electrons, like they are being given off or being lost, is why the electrons find themselves on the product side of the equation. So that is the one way that you can sort of represent the formation of a cation in an equation form by writing something that looks like that. And again here, if we were to name this guy, our name cations, we just use the whole name of it. So magnesium here would be called the magnesium ion. If we had Na+, this would be the sodium ion. So we just use the whole name. We put ion at the end of it. And again, if it's a positively charged cation, if we're going to sort of name it, that is sort of typically how we go about naming it. As we can see here in these examples, sodium, the sodium ion, calcium, the calcium ion, aluminum, the aluminum ion, they're all positively charged. And these are for our representative guys. That is how we go about naming them. If we had something that was in a transition metal, we actually do it a little bit different. Say we have iron with a +2 charge. We would call this the iron Roman numeral 2 ion. And the 2 is for the charge on it. And the reason we need to use the Roman numeral here is iron has the ability to be the iron 2, and iron in some cases could be the iron 3 ion. So because iron has the ability to make multiple positive charges, when we name something, that's usually the guys in the transition metals have the ability to do that. We do use those Roman numerals in addition to identify the charge that we're dealing with. We don't need that on something like sodium. Sodium, no matter what the deal is, it could only form a +1. So it has a fixed charge. So that's why we don't need to include any type of Roman numeral on anybody like that. So if you look on the periodic table, everybody in group 1, 2, and 3, and for group 3, usually it's just aluminum we're talking about. Everybody in group 1 will form a +1 charge. Everybody in group 2 will form a +2 charge. Everybody in group 3 on the periodic table, and again, usually just aluminum there, will form a +3 charge. They have fixed charges. They'll never form anything other than those charges. And there's also some transition metals that will also have fixed charges. Silver has a fixed charge. Always going to be +1 when it forms a charge. Zinc will always be +2 when it forms a charge. It's fixed. And cadmium, if you go right underneath zinc on the periodic table, also has a fixed charge. So if you come across any metal that's in those groups, group 1, group 2, group 3, or if it's silver, zinc, or cadmium, if you want to kind of name them, you just simply use the whole name and ion at the end of it if it's just the ion by itself. But if you have something that's a transition metal, like iron, like copper, like nickel, even lead, which is a little bit outside, or tin, which is SN, you do need to usually put a Roman numeral on those because they have a variable type of charge. Question on that? Okay. Now, anions, on the other hand, is when we do gain electrons. So here an electron is being gained by chlorine, and it becomes a negative charge. And the way that you could represent this in sort of an equation form is electron plus chlorine gives you chlorine with a negative charge. Here, the electrons on the reactant side. So it is like this electron is being gained by the chlorine that has no charge, and it becomes something with a charge on this side. So this is a way in a sort of equation form or reaction form that you could represent the gaining of electrons here. And our guys that typically will gain electrons are our nonmetals, are ones that will gain electrons. and become negatively charged. Any questions on that there? Now, when we name nonmetals, we drop the last part of the name and put IDE on it. So Cl minus goes from chlorine to chloride, IDE ion. You have something like oxygen goes from oxygen to the oxide, IDE ion. You have something like Br minus goes from bromine to bromide ion. So a nonmetal that has gained an electron has a negative charge. If we're just going to name the ion by itself, you drop the last part of the name and you put IDE at the end of it. And here are some examples. Again, fluorine becomes fluoride, IDE. Sulfur becomes sulfide, IDE. And nitride becomes nitrogen becomes nitride, IDE. Now, when we talk about our nonmetals, we have 3, 4, 5, 6, 7, 8. Our nonmetals, again, above the staircase, the guys above that staircase, starting in group number 5, they typically will form a -3 charge. Guys in group 6 will form a -2 charge. Guys in group 7 will form a -1 charge. Again, our nonmetals go that way. So on the periodic table, it's like +1, +2, +3, skip -3, -2, -1 in terms of the charge when you go there. So these are the common charges that these guys will make. Our nonmetals, -3 for group 5, -6, -2 for group 6, and -1 for group 7. Any questions on that there? So an ion is formed by either subtracting electrons or adding electrons from them. So either adding or subtracting electrons from an atom would be the correct answer. Again, when we lose electrons, we become positively charged. When we gain electrons, we become negatively charged. Yeah. Which of the following statements are true? The number of protons is the same for all neutral atoms of an element. That is true. The number of electrons is the same for all neutral atoms of an element. That one is true. The number of neutrons is the same for all neutral atoms of an element. That one is not true. Again, the existence of isotopes, which have different numbers of neutrons, is essentially what isotopes are. So in this case, it would be only 1 and 2 being correct here. Any questions on that one? An ion with a +3 charge that contains 23 electrons. Which ion is it? So again, you do have a ion that is positively 3 charged. So when we look at this guy, it means that it has 23 electrons at this point, but it means that the neutral guy, which is where we would want to find the element, has lost 3 electrons. That's what the positive means. That's what the 3 means. So if we add back those 3 electrons, the correct number of protons in this case would be 26 protons. 26 positives, 23 negatives gives us that +3 that's left over. And that means that 26 is the atomic number, and that should mean it is iron with a +3 charge, as that would be our atomic number. So remember, because we have these 23 negatives, in order to get us a +3 positive, we need 26 positives there to do that. And that'll give us our +3 charge. Any questions on that? So sometimes you got to make sure you don't go with the 23 as your number in this particular case, because again, that's your electrons. And again, it's the protons that tell you how much or what element you're talking about. So as I mentioned earlier, here are some of the charges on the for some of these guys. Again, group 1, which is our alkali metals, they all form +1. They all have a fixed charge no matter what the situation is. Group 2, which is right next door, the alkaline earth metals, everybody in there, calcium, barium, all those guys will always form a +2 charge. Halogens, which is group 7, -1 charge. And the noble gases are perfectly fine the way they are. They really don't want any charge. So it will be 0 in terms of their charge. And here's a prettier picture of what I was just talking about. So again, +1 fixed charge for group 1, +2 for 2. And, usually we talk about here aluminum, but the gallium, those guys. Cadmium also has a fixed charge of +2, zinc and silver. These guys are typically -3 in group 5, -2 here, and -1. So again, +1, +2, +3, skip, and then go backwards, -3, -2, and -1 here in our non-metal region. Remember, the staircase kind of comes down this way. So we're talking upper right of that staircase and our non-metals. Any questions on that? Again, transition metals can make multiple types of charge. So our iron, again, could be something like +2 or +3. Same thing with copper. And then some of these guys over here that are not technically transition metals, things like tin, antimony, lead, bismuth, in this sort of area of the periodic table, they can have a variety of charges as well. So they're oftentimes sort of named like transition metals, which means you do need some Roman numerals. So I know we're a little bit over. We just have a few more slides to go. So I think we're just going to finish it here and we'll start lab. But maybe just we'll take a little break afterwards. When the halogens are typical nonmetals, they typically will gain electrons or accept electrons, and the halogens, which is group 7, so as we just saw there, group 7 should form a -1 charge, and since they are nonmetals, they're going to accept electrons. So it looks like it should be B here would be the correct answer. Any questions on that there? Now, when we do look at things like ionic compounds, and ionic compounds, always when we take a metal and a non-metal together, and what ends up happening is the metal will transfer electrons from the metal to the non-metal, and the metal will become a cation, which is our positively charged guy, and our non-metal will accept the electrons and become our anion and our negatively charged guy. And what holds an ionic compound together is basically the opposites attract. So that positive-negative attraction, that positive and negative attraction, which is referred to as electrostatic attraction, is really what kind of holds that together. There's absolutely no sharing of electrons in an ionic compound. So no sharing of electrons. There's a complete transfer of electrons from the metal to the non-metal, which is creating those charges that we see. So typically ionic compounds have high melting points. They do conduct electricity if they're melted or dissolved in water, but not in the solid state. So they don't really conduct electricity until they dissolve, because when they dissolve, they will break apart into those ions with charges are floating around. And that's really what helps sort of conduct electricity and stuff like that in sort of an ionic compound. All right, I think before we go too far, we'll stop here and we'll start lab about 12:05, take a little break and all that good stuff. And I think what we're going to do is we just have a few more slides here. So I think we'll just finish the last 4 slides or something in lab. It'll probably relate to the lab as well. So we'll talk about that, finish it up. We'll talk about the exam and all that kind of stuff as well, what's going to be on it and when it's going to be and all that kind of stuff as well. So make sure you put here if you didn't do so. I'll see everybody about 12:05 in lab, and we'll wrap up the rest of this up.